Hello ladies and gentlemen, this is Mr. Abdul Karim and I'm going to continue lesson 25.1 in this online session. Honestly, we studied in the previous session how can we generate an induced current or induced voltage, which is called electromotive force and circuit, without using a source of voltage, or only using a wire and a magnet and coils, and moving this magnet perpendicular to the coil or with an angle not parallel or stationary. So we are going to solve a small example about the previous exercise. Calculate the electromotive force induced along a 20 kilometers long conductor. So the length is 20 kilometers. We have to change it into meters. From kilometers to meters, multiply by 1000. So it's gonna be 20,000 meters. That is moving with the orbital speed. So the velocity is 7,800 meters every second. Perpendicular, this means that the angle theta is 90 degrees. The magnetic field is 50 micro Tesla. From micro Tesla to Tesla, just multiply by 10 negative 6. So it's gonna be 50 times 10 negative 6 Teslas. So the formula that we are going to use now is what is EMF is equal BLV sine theta. So EMF is equal to B, which is 50 times 10 negative 6, L, that's 20,000, V, 7,800, sine 90, and calculate it using a calculator. I am going to calculate it right now. So calculator, 50 times 10 power negative 6 times 20,000 times 7,800, it's gonna be 7,800 volts. This means that if you have a long conducting wire of length 20 kilometers and you are moving with let's say airplane, very fast airplane with a speed of 7,800 kilometers, and you have this conducting wire from the window perpendicular to the earth, it will give you a voltage of 7,800 volts. So we are inducing current, or we are inducing voltage, we are producing voltage without a voltage source. Now we are going to the right hand rule, which is about the direction of current using the right hand rule. Put your right hand as the gun, as we took it before in the previous session. Your thumb represents the direction of the velocity. This is the thumb. This is the direction of the velocity V. The index of your finger is the magnetic field P, and the middle finger is the induced current. So VBI. V is the thumb, B is the index, and I is the middle finger. I'm going to give you a small example about this idea. Here, suppose you have wire. This is a wire, This is the wire, and this is the wire. It's connected to a resistor R, and you have here a rod of length L from here to here. Okay, this rod is moving to the right. This is the velocity V, and the magnetic field is into the page. This is B. Okay, so in order to find the direction of the induced current in the circuit, we have to use this right hand rule, which is V B I. So put your thumb, which is V, to the right. Okay, your thumb is to the right. The magnetic field is X into, so thumb to the right, index into the page. Then the current is upward. This is the current I. When the current reaches this region, it will move like this. Then it will continue like this, like this. This is the direction of the induced current. So your thumb is to the right because it represents the velocity. The index is into the page because it represents the magnetic field. So the middle finger is up because the middle finger represents the current. So I is upward, and to make a closed circle like this, like this, like this, like this, like this. Clear? So here we are going to take some examples about sources of mechanical energy. In case of wind turbines, the source of energy is the wind that causes the turbines to spin. We all see these turbines. These turbines work on a phenomena which is transforming mechanical energy into electrical energy. Some countries like Sweden, like Denmark, they use these wind turbines because they produce a large amount of voltage from the rotation of these turbines. This is the rotation. For example, the mechanical energy is transformed into electrical energy. Okay, the turbines are attached mechanically to an armature in the magnetic field. As the armature rotates, an electromotive force is induced in each loop. When the generator is connected to an external circuit, the electromotive force produces current. So these turbines transforms the mechanical energy or the rotation of the turbines into what? Into an electrical energy. Now we are going to move to the generators. We have two types of generators. The first type, which is called the DC generator, and the second type, which is called the AC generator. DC generator, it's direct. D represents direct. C, current, direct current generator. This means that the current in case of DC is constant. We can say that current is 2 amperes. Current is 3 amperes, current is 5 amperes. It's constant, it's steady, it's not changing, it's not reversing direction. It has only one direction and it's not changing direction. While the second one, which is AC generators, it's alternating current. What is the difference between DC and AC? In case of DC, as I said, if you want to draw a graph between the current and time, the graph is like this, constant, always. While in case of AC, if you want to draw the current between a graph between the current and the time, the current is like this. This is what we call a sine function, because this is the function of sine. Sine function means if we see here the current is increasing. Now here it's decreasing. And so on. This means that the current reverses direction. Sometimes the current is moving in the positive direction, sometimes the current is moving in the negative direction. This is an example of DC generators. We took it before as the simple motor. Charges moves in a single direction as they do in batteries. Current moves in one direction because the wires of the armature are connected to a circuit by means of a commutator. We took this example before. We can see that the magnetic field here is directed from right to left. This is B. This is B. And this is the positive pole. So the current is moving like this, from the positive, like this. By using of the right hand rule, we can see that the coil will rotate. Now, this is an example of AC generator. AC generator, alternating current generators can slip ring device to connect wires to a circuit. In this device, one ring is connected to one end of the armature and the other ring is connected to the other end of the armature. Here, the difference between AC and DC is that in case of AC, the current that is moving through the armature, through this armature, this one, is reversing direction only. So the coil will rotate in this arrow direction like this, which is clockwise. As the armature rotates through 180 degrees, the induced electromotive force reverses direction. The power produced by an AC generator is the product of the current and the potential difference. We all know that power is equal I times delta V. The power is always positive because I and V are either both positive or both negative. Average power is half equal to the maximum power. Right. Now I'm going to define what's effective voltage, effective current, and what's average power. نحن we receive a voltage in our homes to 120 volts. Right? This voltage is the effective voltage. Or we can write it like this, delta V effective. But honestly, the company sends us a voltage more than 220 voltage. The voltage that the company sends for us is called delta V max. This is the voltage of the company. So the effective is the voltage that we receive in our homes, and the max is the voltage that the company sends for us. The same idea for the speed of internet that we receive in our homes. We subscribe with, let's say, internet of speed 50 megabytes per second. We receive 47 megabytes per second. 50 is the maximum and the effective is 47. How can we calculate it? We can calculate it using the two formulas here, I effective and V effective. So I effective is equal to 707 I max, and the delta voltage effective is equal to 0.707 delta V max. Let's take a small example about this idea. Suppose the voltage effective of our homes is equal to 220 volts. Find the maximum voltage. So we can say the second formula here, which is delta V effective is equal to 0.707 delta V max. Delta V effective is equal to 0.707 delta V max. 220 is the voltage effective, so 220 equals 0.707 delta V max. So shift solve, I think it's 310. I will check it using the calculator. So 220 over 0.707, that's 311. It's 311 volts. This means that the company gives 311 volts, and we receive 220 volts. We receive 220 volts. Okay, another example for the current. Suppose another example concerning the current. Suppose the current I max is, let's say, 4 amps. Find the effective current. So we use the same formula. I effective equal I max, or 0.707 I max. This means that I effective equals 0.707 times 4. So the answer is gonna be 0.707 times 4, 2.82. 2.82 amperes. Okay, I will solve another exercise about the power, which is here. This formula, P average is equal to half P max. Example, suppose the company, electric company, sends 311 volts as a maximum voltage and 48 amperes as a maximum current. Find the average power. We all know that the average power is defined as half the maximum power. So how can you find P max first? P max, it's I max times delta V max. P is I times delta V, but max, it's max max. So P max is equal to I max, which is 48 times 311. So the answer is gonna be 48 times 311, 14928 watts. So the average power, it's equal to half P max, which is 14928. So the average power is gonna be 7464 watts. Okay, so this is everything that we have to take in this semester. Thank you, and please keep safe.